In the vast, endless void of space, where darkness stretches infinitely in all directions, an ancient question lingers, a question so profound that it transcends time, culture, and human understanding. Who or what created the universe? Is our existence the product of mere cosmic chance, a consequence of cold, indifferent physical laws governing an unfeeling reality? Or is there something greater, something beyond what we can perceive, an intelligence or force that set everything into motion? For centuries, philosophers, scientists, and theologians have struggled to answer this question, proposing ideas that range from divine creation to infinite cycles of birth and destruction, from higher dimensional realities to simulations so perfect that the very notion of real becomes meaningless. Modern science has given us the most widely accepted explanation, the Big Bang Theory, which posits that approximately 13.8 billion years ago, everything we now observe in the cosmos of our galaxy, every star, every atom was once compressed into an unimaginably dense, infinitely small singularity, a point where all known laws of physics break down, and from which the universe suddenly and violently expanded. This idea, supported by overwhelming observational evidence, such as the cosmic microwave background radiation, the redshift of distant galaxies, and the precise ratios of primordial elements, offers an elegant, yet deeply unsettling implication. Before this event, there was no space, no time, no matter, no energino, before, as we understand it. But this leaves us with an even greater mystery. Why did it happen? What caused the Big Bang, if cause and effect as we know them may not even apply to such a moment? Could it have been a random quantum fluctuation arising from a deeper, unknown framework of reality? Or was there some guiding force, an external entity, a consciousness beyond our comprehension that willed it into existence? Some theories suggest that the Big Bang was not the beginning at all, but merely a transition, a rebirth following the collapse of a previous universe in an eternal cycle of expansion and contraction, a concept known as the cyclic universe model, where time is not linear but circular, and the cosmos undergoes infinite cycles of creation and destruction. Others propose the existence of a multiverse, an infinite number of parallel realities branching off from each other, where different physical laws, constants, and even forms of life might exist, making our universe just one among countless others. But if that is the case, what lies beyond the multiverse? What is the fundamental origin of everything? The very fabric from which existence itself is woven. Some physicists turn to quantum mechanics, where strange and counterintuitive phenomena occur, particles appearing and disappearing seemingly from nothing, entanglements that defy our classical notions of space and time, probabilities that suggest reality is not fixed but fluid, dependent on observation. If quantum fluctuations can create particles spontaneously, could an entire universe be born from such an event? The Hartle-Hawking model, for example, proposes that the universe is a self-contained entity with no need for an external cause, existing in a state where time, as we understand it, is meaningless at the singularity, making the question of before irrelevant. Yet even this does not fully satisfy our relentless pursuit of understanding, because if the laws of quantum physics allow universes to emerge from nothing, where did those laws themselves come from? Why do the fundamental forces of nature, gravity, electromagnetism, the strong and weak nuclear forces, have the precise values they do? Values that allow for the formation of stars, planets, and ultimately life itself? The fine-tuning argument suggests that even the slightest change in these constants would render the universe lifeless, leading some to argue that such precision implies an intelligent designer, a force that deliberately set the parameters of existence. Could we be living inside a grand simulation, an experiment created by a higher intelligence, perhaps an advanced civilization from another plane of existence, running a cosmic program so complex that even we, as conscious beings, are merely lines of code within a computational matrix? Visionaries like Elon Musk and physicists exploring digital physics entertain the possibility that what we perceive as reality is nothing more than an illusion generated by a hyper-advanced intelligence, where the fundamental components of our universe are not particles, but information itself. But if we are simulated, then who or what created our creators? Does the chain of creation extend infinitely, or is there an ultimate architect at the highest level, an entity beyond existence as we know it? If so, is this being conscious, personal, aware of us, or is it simply an impersonal force, like a cosmic algorithm running on its own, shaping realities without intent? Some turn to religious and spiritual interpretations, seeing in our universe the fingerprints of a divine creator, a being that exists outside time and space, eternal and infinite, beyond the reach of science, yet deeply ingrained in the human soul. But others argue that such beliefs are merely a reflection of our own desire for meaning in an indifferent cosmos, a way to cope with the unsettling idea that we might be nothing more than a temporary fluctuation in an endless sea of randomness, a brief flicker of consciousness in a universe that neither knows nor cares about our existence. And yet, despite all our uncertainties, one thing is clear: the search for the ultimate truth continues. Scientists develop ever more powerful telescopes, peering deeper into the universe's past, hoping to glimpse the very moment of creation itself. Physicists probe the deepest layers of reality, smashing particles together in immense accelerators to uncover the fundamental building blocks of existence. Mathematicians explore theories that stretch the limits of logic, seeking equations that might finally unlock the secrets of the cosmos. Philosophers debate the nature of reality, consciousness, and meaning, wrestling with questions that may never have definitive answers. And we, as individuals, continue to wonder, to question, to dream, drawn by an insatiable curiosity that has defined humanity from the very beginning. Perhaps one day, we will uncover the answer to the greatest mystery of all. Perhaps we will discover the origin of the universe, the reason for existence, the truth behind everything, or perhaps the answer is beyond our reach, forever hidden behind the veil of reality, waiting for a mind far greater than ours to comprehend. But until then, we keep searching, driven by the unshakable belief that somewhere, somehow, the answer is out there, waiting to be found.
For millennia, humanity has looked up at the night sky, wondering about the nature of the cosmos, struggling to make sense of the stars, planets, and the vast unknown that stretches infinitely beyond our grasp. And while ancient civilizations had their own explanations, often rooted in mythology and divine intervention, the quest for understanding the universe has been an evolving journey, shaped by curiosity, observation, and scientific breakthroughs. Early societies, such as the Babylonians, Egyptians, and Chinese, observed the heavens meticulously, creating some of the first star charts and calendars, which were essential for agriculture, navigation, and religious practices. Yet their understanding of the cosmos remained deeply intertwined with mythology, where celestial bodies were often considered deities or divine messengers. The ancient Greeks, however, took the first steps toward a more systematic, rational approach to cosmology, with philosophers such as Pythagoras proposing that the Earth was a sphere rather than a flat plane, an idea later supported by Aristotle, who cited evidence such as the curved shadow of the Earth on the Moon during lunar eclipses. Around 300 BCE, Aristarchus of Samos went even further, suggesting that the Sunday, not the Earth, was at the center of the universe, though this heliocentric model was largely dismissed in favor of the geocentric system of Ptolemy, which dominated astronomical thought for over a millennium, with the notion that Earth was the fixed center of all celestial motion, deeply ingrained in both scientific and religious doctrine, reinforced by the teachings of the Catholic Church. It was not until the 16th century that this paradigm was challenged in a revolutionary way by Nicolaus Copernicus, who revived the heliocentric theory, arguing that the Earth and other planets revolved around the Sunday, a radical idea that faced fierce opposition but laid the foundation for the scientific revolution. This shift gained momentum with Johannes Kepler's laws of planetary motion, which described the elliptical orbits of planets, and Galileo Galilei's use of the newly invented telescope, which allowed him to observe moons orbiting Jupiter, craters on the Moon, and the phases of Venus, further discrediting the Ptolemaic model and providing direct evidence for a Sunday-centered system. The next major leap came with Isaac Newton's formulation of the laws of motion and universal gravitation in the late 17th century, explaining that celestial bodies move according to predictable physical laws, unifying terrestrial and cosmic mechanics under a single framework, marking a turning point in humanity's understanding of the universe as something governed by natural principles rather than supernatural forces. For centuries, astronomy continued to develop, with new telescopes revealing more about the Milky Way, and by the 20th century, the discovery of other galaxies by Edwin Hubble shattered the long-held belief that the Milky Way was the entire universe, as he observed that galaxies were receding from us, leading to the groundbreaking realization that the universe was expanding, a concept that formed the basis of the Big Bang Theory. Proposed by Georges Lemaitre and later confirmed by Hubble's observations of redshift, the Big Bang Theory suggested that the universe had a definite beginning, emerging from a hot, dense singularity approximately 13.8 billion years ago, challenging the previously accepted notion of a static, eternal cosmos. This was further supported by the discovery of the cosmic microwave background radiation by Arno Penzias and Robert Wilson in 1965, an afterglow from the early universe that provided critical evidence for the Big Bang, cementing it as the leading cosmological model. As scientific progress accelerated, breakthroughs in quantum mechanics and general relativity provided deeper insights into the fabric of spacetime, with Einstein's equations predicting phenomena such as black holes, gravitational waves, and the warping of time under extreme gravitational forces, concepts that were once purely theoretical but later confirmed through astronomical observations and experiments. Meanwhile, the space age was dawning, with humanity taking its first steps beyond Earth's atmosphere, starting with the launch of Sputnik by the Soviet Union in 1957, followed by Yuri Gagarin becoming the first human in space in 1961, and culminating in the Apollo 11 mission in 1969, where Neil Armstrong and Buzz Aldrin walked on the moon, a historic milestone that marked the beginning of space exploration as a tangible reality, rather than a distant dream. Over the following decades, space agencies like NASA, ESA, and Roscosmos sent probes to study the outer planets, landed rovers on Mars, and launched telescopes like Hubble, which provided breathtaking images and crucial data about the structure and evolution of the universe, revolutionizing our understanding of galaxies, exoplanets, and cosmic phenomena such as dark matter and dark energy. As our observational capabilities expanded, so too did our concept of the observable universe, which refers to the portion of the cosmos that we can see, limited by the speed of light and the age of the universe, currently estimated to be about 93 billion light-years across, even though the entire universe may be far larger, or even infinite. This observable boundary represents the furthest reaches of what light has been able to travel since the Big Bang, providing us with a glimpse into the universe's past, yet also presenting the paradox that some regions will forever remain beyond our reach due to the ongoing expansion of space, driven by the mysterious force known as dark energy. Today, we stand at the precipice of a new era in cosmology and space exploration, with advanced observatories like the James Webb Space Telescope poised to peer deeper into the universe's infancy, upcoming missions planning to establish human colonies on Mars, and theories such as the multiverse, cosmic inflation, and quantum gravity challenging our deepest assumptions about reality. As we continue to seek answers to the fundamental question that has driven humanity for millennia, what is the true nature of the universe? Where did it come from? And are we alone in this vast, incomprehensible expanse? The universe is vast, incomprehensibly vast, stretching far beyond what we can see, beyond what we can measure, beyond even what we can imagine. And in that infinite expanse lies a profound truth that should shake us to our core. We are small, mere specks of dust, floating in a cosmic ocean, fragile, temporary, and yet somehow deeply significant. To look up at the night sky is to confront a reality that is both beautiful and terrifying. A reality that humbles us, yet fills us with an insatiable hunger to understand, to reach beyond our limits, to grasp even a fragment of the infinite. Because in the vast, indifferent universe, we are the only known beings capable of questioning our own existence. And that should matter. It should matter because, despite our smallness, we care, we wonder, we dream, and that relentless curiosity has propelled us from primitive beings huddled around fires to explorers of the cosmos, sending robotic emissaries to distant planets, peering into the deepest corners of space, trying to decipher the secrets of existence itself. And yet, for all our progress, we are still haunted by the unknown, by the questions that whisper in the quiet moments, that echo in the spaces between thoughts. Why are we here? How did all of this begin? What, if anything, lies beyond the edge of what we can perceive? These are not just scientific questions. They are deeply personal ones, questions that strike at the heart of what it means to be human, because to explore the universe is, in many ways, to explore ourselves. The cosmos is not separate from us. We are made of it, every atom in our bodies forged in the hearts of ancient stars, scattered across time and space, only to coalesce into thinking, feeling beings who now look back upon the universe that gave them life, trying to make sense of it all. And yet, with that wonder comes an undeniable fear, a fear that gnaws at the edges of our understanding, the fear of the void, of the overwhelming emptiness that lies between the galaxies, of the crushing isolation of a universe so vast that even light itself takes billions of years to traverse it. We are used to a world of connection, of closeness, yet the universe is defined by distance, by separation, by the chilling realization that we may be utterly alone. The thought is suffocating, unbearable even, because if we are truly alone, if life exists nowhere else, then the weight of the universe rests entirely on our shoulders, making us both incredibly special and terrifyingly insignificant. And if we are not alone, if there are others out there, other minds, other beings staring up at their own skies, wondering the same things, then what does that mean for us, for our place in the grand scheme of things? This is why the universe matters, why it is more than just equations, more than just physics and theories and numbers, because it forces us to confront the deepest parts of ourselves, to face the terrifying beauty of existence and embrace it, to stand beneath the infinite, and, instead of shrinking away, to reach toward it, to wonder, to ask, to seek. We are cosmic children, born from the remnants of dying stars, gifted with the extraordinary ability to reflect on our own origins, to contemplate the very fabric of reality. And whether we find all the answers or not, whether we reach the edges of the known universe or remain bound to this small blue world, the journey itself, the questions, the discoveries, the awe, the terror, the endless searches, what makes us who we are. The universe matters because we care. And as long as we continue to care, to wonder, to dream, we will never be lost in the vastness. Because even in the face of the infinite, we are here, we exist, and that, in itself, is the greatest mystery of all. Have you ever stopped to think about where everything came from, not just the stars or the galaxies, but existence itself? Have you ever stared into the night sky and felt something deep inside you stir, a mixture of awe and unease, as if you were standing on the precipice of a great cosmic truth just beyond your reach? What if everything you know, everything you take for granted, time, space, reality itself, is only a small part of a far greater mystery? A mystery that has no clear beginning and perhaps no end. When we talk about the origins of the universe, we are not simply discussing abstract scientific theories or equations locked away in textbooks. We are asking the most fundamental questions about our existence, questions that challenge our deepest assumptions and force us to confront what it truly means to be conscious, to be alive, to be part of something so unfathomably vast that our entire planet is less than a grain of sand in comparison. How does it make you feel to know that, in the grand scheme of the cosmos, you are incredibly small, yet capable of asking the most profound questions ever conceived? And if we are capable of asking them, are we also capable of finding the answers? The universe is expanding, growing larger with every passing second, pushing the boundaries of what we can observe and comprehend. And yet, the more we discover, the more questions arise: what lies beyond the observable universe, beyond the limits of what our telescopes can see? If the universe had a beginning, what came before it? If space and time were created in the Big Bang, then what existed outside of space and time? Could our reality be just one of many, a single thread in a vast, infinite multiverse where different versions of reality play out in ways we cannot even imagine? And if that is the case, then does that mean there are other versions of you, living different lives, making different choices, in worlds where the fundamental laws of physics are entirely alien to our own. If the mysteries of the universe are so vast, does that mean we are destined to never truly understand them? Or is it our purpose to keep searching, no matter how impossible the answers may seem? Every great scientific breakthrough in history once seemed impossible when ancient civilizations first mapped the stars. Did they ever dream that one day humans would walk on the moon? When Galileo turned his telescope to the sky, did he imagine that, centuries later, we would send robotic explorers to Mars, uncovering the secrets of a planet that was once thought to be a distant red dot in the heavens? If we could go from believing the Earth was the center of the universe to discovering that we are part of an ever-expanding cosmic web, what new truths are still waiting to be uncovered? What if the greatest discovery of all is still ahead of us? What if, in our lifetimes, we receive undeniable proof of extraterrestrial life, intelligent beings who have been observing us, waiting for the moment to reveal themselves? How would that change everything we think we know about ourselves, about our place in the universe? Would it unite us as a species, or would it shake our very foundations, forcing us to question everything we have ever believed? And even if we never find aliens, even if we are alone, does that not make our existence even more precious, more extraordinary? Because it would mean that out of all the vastness, out of all the infinite galaxies and endless voids, we are something unique, something rare, something utterly irreplaceable. The next great discovery is coming, whether we are ready for it or not. Whether it is the revelation of what came before the Big Bang, the detection of signals from an advanced civilization, or something even stranger, something we have not yet begun to imagine. How will we respond when the next great cosmic truth is revealed? Will we embrace it with open minds? Or will we fear it, resist it, deny it, because it does not fit into what we already know? That is why this mystery matters, not just for scientists, not just for philosophers, but for every single one of us. Because to question the universe is to question ourselves, and to explore the unknown is to expand the very boundaries of what it means to be human. So now, I ask you, what do you believe? What do you think lies beyond the edge of what we can see? Do you think there is a grand design, an intelligence behind it all? Or do you believe that everything is the result of pure chance, a cosmic accident with no greater meaning? And if that is the case, then does that not mean that we, as conscious beings, are the ones who must create meaning for ourselves? If the universe does not provide answers, then is it not our responsibility to ask better questions, to seek, to explore, to push forward? Because as long as we do, we are defying the darkness. We are fighting against the void. And in doing so, we are proving that our existence, however fleeting, matters. This is not just science, this is our story. The story of how a species that emerged from the dust of dead stars dared to look up and ask, why? And the only way to continue that story is to keep searching, keep wondering, keep questioning. Because the universe is not just something to be observed, it is something to be experienced, to be understood, to be a part of. So now, I leave you with one final question. If you could know the ultimate truth about the universe, if you could understand everything, would you want to? Or is the mystery itself what makes life worth living? In the infinite darkness of the cosmos, where time itself stretches beyond meaning and distance, becomes an abstraction too vast for the human mind to grasp, an ocean of galaxies drifts silently through the void, each one a swirling maelstrom of stars, gas, and dust, bound together by invisible forces that shape the very fabric of reality. The Milky Way, our home, is but a single grain in this cosmic expanse, a barred spiral of over 100 billion stars, its arms stretching outward like celestial rivers winding through the abyss. Yet even our entire galaxy is nothing more than a whisper in the greater symphony of existence. Beyond its luminous core, where ancient stars burn with a relentless fury, lies an endless procession of neighboring galaxies, some colliding in gravitational dances that span eons, others isolated in the emptiness, drifting through the intergalactic void where the distance between them is so immense that even light, the fastest traveler in the universe, takes millions of years to bridge the gap. And in that void, in the spaces between the great galactic structures, lies something even more profound: dark matter, an invisible substance that neither emits nor reflects light, yet exerts an undeniable gravitational pull, shaping the cosmos in ways that defy our understanding. It is this enigmatic force, undetectable by any telescope yet making up the majority of the universe's mass, that binds galaxies together, preventing them from flying apart, a silent architect of cosmic structure, whose very nature remains one of the greatest mysteries in physics. Beyond dark matter lurks an even stranger entity: dark energy, a force that stretches the very fabric of space, driving the accelerating expansion of the universe, an unseen hand pushing galaxies apart faster than gravity can pull them together, ensuring that the cosmos will continue its relentless growth until the stars themselves are nothing more than distant, fading embers in an ever-expanding abyss. This vast, incomprehensible landscape has captivated some of the greatest minds in history, from ancient philosophers who gazed at the stars with nothing but their intuition to modern cosmologists wielding instruments so precise they can detect the faintest whispers of radiation from the birth of time itself. Edwin Hubble, the man who shattered the illusion of a static universe, first saw the spectral shifts in distant galaxies, proving that the universe was expanding, a revelation that changed everything we thought we knew. Albert Einstein, whose equations of general relativity predicted the warping of space and time itself, struggled with the implications of an evolving cosmos, first resisting the idea, then ultimately embracing a vision of reality so profoundly different from classical physics that it continues to reshape our understanding of existence. Then came Georges Lemaitre, a priest and physicist who first proposed what we now call the Big Bang Theory, suggesting that the universe was born from a single, infinitely dense point-a moment of creation that defied all previous conceptions of time and space. And as our technology advanced, new minds took up the challenge, with figures like Stephen Hawking pushing the boundaries of black hole physics, revealing that even the most mysterious and destructive entities in the cosmos slowly evaporate, leaking energy back into the universe in ways that challenge the very foundation of quantum mechanics. Today, our quest to understand the cosmos continues with instruments like the James Webb Space Telescope, peering deeper into space than ever before, revealing galaxies from the dawn of time, their light having traveled for billions of years to reach us, whispering secrets of an era long gone. Particle physicists at CERN smash atoms together at nearly the speed of light, searching for the fundamental building blocks of reality, hoping to uncover the hidden forces that shaped the universe in its first moments. And yet, for all our progress, the great mysteries remain what lies beyond the observable universe, beyond the cosmic horizon where light has not yet had time to reach us. Is our universe one of many, a single bubble in an infinite multiverse, where different physical laws may govern realities so alien we could never comprehend them? And most haunting of all, what is the ultimate fate of everything? The final chapter of this grand cosmic story. Will the universe expand forever, stars burning out one by one until only a cold void remains? Or will some unknown force reverse this process, pulling everything back together in a final cataclysm, a great cosmic reset? As we ponder these questions, we stand on the shores of an ocean so vast we have barely begun to dip our feet into its waters. Yet something deep inside us compels us to push forward, to navigate the darkness, to seek answers in the void. Because the universe is not just a place we inhabit, it is a mystery waiting to be unraveled, a story written in the language of physics, mathematics, and the unyielding curiosity of those who dare to ask, what lies beyond the stars? The deeper we peer into the cosmos, the more we realize how little we truly understand. Each discovery, each new theory, each breakthrough that seems to bring us closer to understanding the universe only serves to reveal new mysteries, new contradictions, new paradoxes that defy logic and challenge the very foundations of what we believe to be true. And perhaps the most unsettling realization of all is that we may never find the true edge of reality, not because it does not exist, but because we may be fundamentally incapable of perceiving it. The universe, as we currently understand it, is bound by rules we can observe but not fully explain. And every attempt to push beyond those boundaries reveals deeper layers of complexity that only raise more questions. Even our most advanced theories, from general relativity to quantum mechanics, seem to be incomplete, providing astonishingly accurate descriptions of reality in certain conditions, but breaking down entirely in others, as if the universe itself is taunting us, revealing just enough to keep us searching but withholding the final truth. Consider the paradoxes that already plague modern physics. Black holes, for example, represent an extreme region of space where gravity becomes so strong that nothing, not even light, can escape. Yet at the heart of a black hole lies a singularity, a point where the laws of physics as we know them cease to function, where space and time collapse into an undefined state that cannot be mathematically resolved. These singularities suggest that something is missing from our understanding, that our current models are insufficient to fully grasp the nature of reality at its most fundamental level. The conflict between general relativity, which describes gravity on the grandest scales, and quantum mechanics, which governs the microscopic realm, further highlights the incompleteness of our theorist woe of the most successful frameworks in scientific history, both extensively tested and confirmed, yet completely incompatible with each other, leading physicists to search for a unified theory of everything that remains elusive despite decades of effort. Even more perplexing is the concept of the observable universe itself, or cosmic horizon, is defined by the speed of light and the age of the universe, meaning we can only see as far as light has had time to travel since the Big Bang. But what lies beyond that horizon remains a mystery, possibly forever hidden from us. The observable universe is not necessarily the full extent of reality. It is merely the portion we can detect, limited by the constraints of space-time and our own position within it. And as the universe continues to expand, driven by the mysterious force of dark energy, more and more of the cosmos is slipping beyond our reach, receding faster than light can travel, ensuring that some regions will forever remain unseen, unknowable, cut off from us, not by distance, but by the very nature of space itself. This presents a chilling possibility that the ultimate truth about the universe may be inherently unattainable, not because we lack the intelligence or the technology, but because the structure of reality itself prevents us from ever perceiving the full picture. We are trapped within our own cosmic bubble, confined to what we can observe, unable to reach beyond the event horizon of our own understanding. Even the concept of time itself is in question. While we experience time as a linear progression from past to future, certain interpretations of quantum mechanics suggest that time may not be fundamental at all, but rather an emergent property of deeper, hidden variables, meaning our entire perception of cause and effect could be an illusion, a limitation of human consciousness, rather than an objective feature of reality. Could it be that our search for the origin of the universe is flawed from the beginning? That there was no beginning in the way we think of it, but rather a state of existence beyond time, beyond causality, beyond anything our minds are capable of grasping? Even if we one day develop a theory that explains every observable phenomenon, how can we ever be certain that it is the final answer? How many times in history have we believed we understood the cosmos, only to have those beliefs overturned by new discoveries? Once we thought the Earth was the center of everything. Later, we thought the Milky Way was the entire universe. Now we accept the idea of an expanding cosmos, but even that may one day be replaced by something even more bizarre, something that forces us to rethink reality itself. The deeper we go, the more our certainty unravels. Perhaps the true edge of the universe is not a physical boundary, but a conceptual one, a limit not of space, but of knowledge, a horizon beyond which our understanding simply cannot extend. If that is the case, what does it mean for our quest to uncover the ultimate truth? If we are forever trapped within the boundaries of what we can observe, will we ever truly know what lies beyond? Or are we destined to search endlessly, always reaching but never quite grasping, always on the brink of understanding yet forever held back by the very structure of existence itself? These questions may not have answers. Perhaps they never will. But the pursuit of those answers, the relentless drive to push against the unknown, is what defines us as a species. Even if we never find the true edge, even if the final truth remains forever out of reach, the act of searching, of questioning, of striving toward the impossible is what makes the journey worthwhile. For centuries, the quest to define the boundaries of the universe has been at the heart of cosmology. Yet every step forward has only deepened the contradictions, tensions, and mysteries that plague our understanding of reality. The conflict is not just between different schools of thought, but between the very nature of observation and theory, between what we can see and measure, and what mathematics suggests must exist. On one side are those who argue that the universe is infinite, stretching endlessly beyond the limits of our observation, a boundless expanse of galaxies, energy, and perhaps even parallel realities, where no true edge exists, just an ever-expanding cosmic horizon that recedes as we reach toward it. On the other side are those who believe the universe is finite, that beyond a certain point there is nothing, or perhaps something radically different, a fundamental boundary that we may never reach, but that exists nonetheless, limiting the universe in ways we have yet to understand. This debate has only intensified as our understanding of physics has grown, revealing deep contradictions that seem impossible to reconcile. General relativity, one of the most successful scientific theories ever formulated, describes a universe where space itself bends and warps under the influence of gravity, suggesting that if the universe is curved in just the right way, it could be finite yet unbounded, like the surface of a sphere but in higher dimensions, meaning that traveling in one direction indefinitely could eventually bring you back to your starting point. Yet quantum mechanics, which governs the smallest scales of reality, refuses to fit neatly into this picture, introducing probabilistic uncertainties, virtual particles appearing from nothing, and fundamental limits to what can be known with absolute precision, all of which complicate the question of whether the universe truly has an edge. The struggle to define the edge is not just theoretical, it is observational. The observable universe, the portion of the cosmos from which light has had time to reach us, has a definable boundary, currently estimated at around 93 billion light-years across. But this is not the actual size of the universe, only the part we can detect. Beyond this horizon, galaxies and entire structures may exist, but they are receding so quickly due to cosmic expansion that their light will never reach us, making them effectively unreachable and, for all practical purposes, non-existent to us. This creates an inherent tension in cosmology. If we can never observe beyond a certain point, can we ever truly know whether the universe extends infinitely, or are we forever trapped within the limits of our own observational bubble? This conflict has led to competing explanations, each attempting to resolve the contradictions, but often raising more questions than they answer. The multiverse hypothesis suggests that our universe is just one of many, a bubble in an endless sea of other universes, each with different physical laws and properties, meaning that what we perceive as the edge is merely the boundary of our particular cosmic region, beyond which entirely different realities may unfold. String theory, an ambitious but unproven framework that attempts to unify general relativity and quantum mechanics, proposes extra spatial dimensions curled up at microscopic scales, hidden from us but fundamental to the fabric of reality, possibly offering a new way to think about cosmic boundaries, or even eliminating the need for a traditional edge entirely. Meanwhile, theories of a cyclic universe suggest that the cosmos is not expanding infinitely, but rather oscillating, going through cycles of expansion and contraction, meaning the Big Bang was not the beginning, but just one of many phases in an eternal cosmic rhythm. Yet all these ideas remain speculative, lacking definitive observational proof, clashing with each other and with existing evidence, leaving cosmologists in a perpetual struggle to reconcile competing perspectives. Even the question of cosmic expansion presents a conflict while we know the universe is expanding. The discovery that this expansion is accelerating, driven by the mysterious force known as dark energy, has thrown previous models into disarray, challenging our very assumptions about the fate of the universe. Will it continue to expand forever, thinning out into an empty void where stars burn out and black holes evaporate, leaving behind a cold, dark nothingness? Or will the expansion reverse, leading to a final collapse, a big crunch, where everything is pulled back into a singularity, only to explode outward again in a new cycle of creation and destruction? Each possibility is supported by certain models, yet contradicted by others, with no clear resolution in sight. The tension between observable evidence and theoretical models is perhaps the greatest challenge in modern cosmology. Each new discovery, from the detection of gravitational waves to the mapping of the cosmic microwave background, provides crucial insights, but also exposes new gaps in our understanding, forcing us to revise, refine, or sometimes even abandon long-held theories. The universe is not revealing its secrets easily, and every attempt to define its boundaries only seems to highlight the limits of our knowledge, pushing us toward the unsettling possibility that the final answers may forever remain beyond our reach. The edge of the universe, whether physical, conceptual, or both, remains the ultimate frontier, a challenge that defies simple explanations, demanding a new way of thinking, a new level of understanding that we may not yet be capable of achieving. And so the struggle continues, the search intensifies, and the great cosmic conflict, the battle between what we know, what we theorize, and what we may never be able to grasp remains unresolved, driving us ever forward in our quest to define the undefinable, to reach beyond the limits of perception, to uncover the ultimate truth about the nature of existence itself. If the universe has no edge, if it truly stretches on forever in an infinite expanse, then we are forced to confront one of the most profound and unsettling possibilities ever considered by the human mind, that existence itself has no boundary, no final frontier, no definable limit, meaning that our understanding of reality is fundamentally incomplete. The implications of an infinite universe shake the very foundations of physics, cosmology, and even philosophy, forcing us to reconsider everything from the nature of space and time to the very concept of meaning and existence itself. If there is no edge, then what does that say about our understanding of physics? A field that has always sought to define things within measurable limits. General relativity has given us an extraordinary framework for describing the curvature of space-time, the motion of planets, the structure of galaxies, and the behavior of black holes. Yet it has never been tested against the idea of an infinite universe in a truly rigorous way. If space extends forever, does that mean it is truly uniform, following the same laws and principles everywhere? Or does infinity itself introduce new and unpredictable structures that defy our current theories? Could there be regions of space where the constants of physics are different? Where gravity behaves in ways we have never imagined? Where the very fabric of reality follows rules so alien that they might as well belong to another universe entirely? And if so, does that mean our universe is not a single, cohesive entity, but rather an endless patchwork of different physical realities, stitched together in ways that our current models cannot even begin to describe? If the universe has no edge, then our quest to understand it may never truly end. No matter how much we discover, there will always be more. An infinite number of galaxies beyond the ones we can see, an infinite number of structures beyond the ones we can map, an infinite number of mysteries beyond the ones we can solve. This presents a paradox of knowledge. For in an infinite universe, can we ever claim to fully understand anything? If there are an infinite number of galaxies, does that mean there are an infinite number of Earth-like planets? An infinite number of civilizations? An infinite number of versions of ourselves, living out an endless array of different possibilities? The multiverse hypothesis suggests that not only is the universe infinite in space, but it may also be infinite in variation, meaning that every possible outcome of every event could be playing out somewhere, in some distant region of space-time, where another version of you might be making different choices, living a different life, experiencing a reality that is both familiar and fundamentally different. But if that is true, what does it mean for our sense of identity, our sense of uniqueness? If there are infinite versions of us, does that mean individuality is an illusion? That we are not singular beings, but rather fragments of a larger infinite system, endlessly replicated across space and time? And if everything that can happen is happening somewhere, does that mean that nothing is truly special? That no event, no discovery, no life is unique? The existential weight of this idea is staggering, as it challenges the very meaning of existence itself. If everything that can happen does happen, then is there any purpose to anything at all? But even beyond the philosophical implications, the idea of an infinite universe forces us to confront a profound problem in physics. Our current theories are not equipped to handle infinity. Quantum mechanics, which governs the smallest scales of reality, breaks down when applied to infinite systems, leading to paradoxes and unsolvable equations that suggest we are missing something fundamental. General relativity, for all its successes, cannot describe the behavior of space-time at the quantum level, leaving us without a complete picture of the fundamental forces that shape the cosmos. If the universe is infinite, then it demands new physics, new models that go beyond what we currently know, theories that can account for the full complexity of an unbounded reality. This is why physicists search for a theory of everything, a unifying framework that can bridge the gap between relativity and quantum mechanics, that can explain how the fabric of space-time behaves at the smallest and largest scales, that can reconcile the contradictions between an infinite universe and the finite tools we have to measure it. Perhaps this new physics will come from string theory, which proposes that the fundamental building blocks of reality are not particles but vibrating strings of energy, existing in higher dimensions beyond our perception. Or perhaps it will come from loop quantum gravity, which suggests that space-time itself is made of discrete, quantized units, a fabric woven from fundamental bits of information, eliminating the paradoxes of infinity by imposing a deeper, hidden structure to reality. But until such a theory is found, we remain in a state of uncertainty, caught between the known and the unknown, between the observable and the theoretical, between the finite and the infinite. If the universe has no edge, then the ultimate question becomes, can we ever truly understand it? Are we, as finite beings with finite lifespans, capable of grasping the full scope of an infinite cosmos? Or are we doomed to forever glimpse only fragments of the greater whole, always reaching but never quite touching the truth? And if that is the case, what does that mean for our search for meaning? For our quest to find our place in the universe? Perhaps the greatest consequence of an infinite universe is the realization that the journey will never end, that there will always be more to discover, more to explore, more to understand. And maybe, just maybe, that is the point, not to find a final answer, but to continue the search, to embrace the mystery, to stand beneath the infinite sky, and, instead of fearing its vastness, to find wonder in the fact that we are here at all, conscious beings in an endless cosmos, daring to ask the impossible questions. There have been moments in the history of science when everything changed, when a single discovery reshaped our understanding of the universe so profoundly that we could never see reality the same way again. These turning points define the progress of cosmology, marking the transition from speculation to knowledge, from ignorance to insight, from merely observing the cosmos to beginning to understand its fundamental nature. One of the greatest of these moments came when Edwin Hubble, using the powerful telescopes of the early 20th century, discovered that the universe was expanding. Before this revelation, the prevailing assumption among scientists and philosophers alike was that the cosmos was static, eternal, and unchanging. But Hubble's observations of distant galaxies showed something unexpected. Their light was redshifted, meaning they were moving away from us. And the farther they were, the faster they seemed to be receding. This discovery shattered the long-held belief in a steady, unchanging universe and set the foundation for the Big Bang Theory, which proposed that the universe had a beginning, a moment of creation from an infinitely dense singularity that has been expanding ever since. However, the implications of this revelation led to even deeper mysteries. For if the universe was expanding, what was driving this expansion? And what would its ultimate fate be? For decades, cosmologists assumed that the combined gravitational pull of all the matter in the universe would eventually slow down this expansion, perhaps even reverse it in a final cataclysmic collapse known as the Big Crunch. But then came another moment that changed everything, perhaps the most shocking and unexpected discovery in modern cosmology. In the late 1990s, two independent teams of astronomers studying distant supernovae to measure the rate of cosmic expansion found something that defied all expectations. The expansion of the universe was not slowing down, but accelerating. This discovery, awarded the Nobel Prize in Physics in 2011, revealed the presence of a mysterious force that had never been accounted for: dark energy, a hidden influence that makes up nearly 70% of the universe's total energy and is literally pushing space itself apart. This single revelation upended everything we thought we knew about cosmology, raising more questions than it answered. What is dark energy? Is it a property of space itself? A fundamental energy that arises from the fabric of the cosmos? Or is it something deeper, a force that emerges from a hidden layer of physics we do not yet understand. And most importantly, what does it mean for the fate of the universe? If dark energy continues to dominate, then the universe will keep expanding forever, growing colder and darker as galaxies drift apart, stars burn out, and the cosmos becomes an empty, frozen void in what scientists call the heat death scenario. But what if dark energy changes over time? Could it eventually reverse, leading to a collapse? Or could it intensify, tearing galaxies, stars, and even atoms apart in a final catastrophe known as the Big Rip? The search for answers has driven some of the most ambitious scientific projects in history, with technological advancements pushing the boundaries of what we can observe. The Hubble Space Telescope, launched in 1990, has allowed astronomers to see deeper into the universe than ever before, capturing light from galaxies billions of light years away, effectively looking back in time to the earliest moments of cosmic history. It revealed not only the large-scale structure of the universe, but also helped refine our measurements of the Hubble constant, the rate of cosmic expansion. Leading to yet another paradox. Different methods of measuring this rate give conflicting answers, suggesting that something fundamental about our understanding of cosmology may be incomplete. But Hubble was only the beginning. In 2021, the launch of the James Webb Space Telescope, JWST, marked a new era of discovery, with its infrared capabilities allowing it to peer through cosmic dust and detect the earliest galaxies formed after the Big Bang. Within months of operation, JWST had already surprised scientists by finding massive, mature galaxies at times when the universe was supposed to be too young for such structures to exist, challenging existing models of galaxy formation and suggesting that something about our understanding of early cosmic evolution may be missing. These telescopes, along with upcoming missions like the Nancy Grace Roman Space Telescope and the Euclid Telescope, are not only refining our understanding of dark energy, but are also probing the nature of dark matter, another enigmatic substance that makes up 27% of the universe yet has never been directly detected. Unlike normal matter, which interacts with light, dark matter is completely invisible, revealing itself only through its gravitational influence on galaxies and cosmic structures. Without it, galaxies would not hold together. They would spin apart due to their own rotational speed, yet despite its undeniable effects, no known particle in the standard model of physics accounts for it. This suggests that dark matter is either made of unknown, undiscovered particles, or that our very laws of gravity require modification. An idea that challenges the foundations of physics itself. The Large Hadron Collider at CERN has been attempting to recreate conditions similar to those just after the Big Bang in the hopes of discovering a dark matter particle. But so far, the search has turned up nothing definitive, deepening the mystery further. As we continue to push the boundaries of observation and theory, new questions arise that may point toward an even deeper revolution in physics. Quantum mechanics and general relativity, the two most successful scientific theories ever developed, remain fundamentally incompatible, meaning that our understanding of gravity at the quantum level is incomplete. Could dark energy and dark matter be hints of a larger, more profound theory of reality that we have yet to discover? Could there be extra dimensions beyond the three of space and one of time that we experience? Could the true nature of the universe lie in something even more exotic holography, where reality as we perceive it is just a projection from a deeper, hidden realm? Perhaps the biggest lesson from these turning points is that every time we believe we are approaching a final answer, the universe reveals itself to be even stranger than we imagine. With every new telescope, every new experiment, we refine our understanding. Yet the ultimate truth remains elusive, always just beyond our grasp. What comes next may be the biggest turning point of all, the moment when we finally see beyond the veil of our current knowledge and step into a new era of physics, one that redefines the very nature of existence itself. For centuries, humanity has attempted to unravel the mysteries of the universe, using a framework based on observation, mathematics, and logic. Yet every time we come close to an answer, we find ourselves faced with deeper, more perplexing questions. What if the problem is not that we lack the tools to understand the universe, but that we have been looking at the problem the wrong way? What if our entire perspective on reality, space, time, and even the fundamental nature of existence is flawed, requiring a radical shift in thinking? a complete reimagining of what the universe actually is. The deeper we dive into the nature of the cosmos, the more we realize that conventional ways of understanding reality may not be enough. One of the most revolutionary ideas in modern physics, the holographic principle, suggests that the three-dimensional universe we perceive may not be fundamental at all, but instead a projection of information stored on a distant, lower-dimensional surface. First proposed in the context of black hole physics, the holographic principle was developed from the realization that the amount of information that can be stored within a black hole is proportional not to its volume, as one might intuitively expect, but to its surface area. This idea was extended by physicists such as Gerard T. Hooft and Leonard Susskind to suggest that perhaps the entire universe functions similarly, that what we experience as a vast, three-dimensional reality may actually be a kind of illusion, encoded on a distant, two-dimensional boundary beyond our observable horizon. If this is true, then the fundamental nature of space and time may be dramatically different from what we have assumed, and the very concept of an edge to the universe may be meaningless, because what we think of as space is merely an emergent property of deeper, hidden information. This perspective forces a re-evaluation of many long-standing questions in cosmology, including the nature of dark energy and the expansion of the universe. If space itself is not fundamental but emergent, then what we perceive as the stretching of the cosmic fabric may not be an outward expansion in the conventional sense, but rather a shift in the way information is encoded on the cosmic horizon. Some physicists even speculate that the accelerating expansion of the universe, which has puzzled scientists since the discovery of dark energy, may be a reflection of changes in the underlying holographic information structure, rather than a force acting within space-time itself. Beyond the holographic principle, alternative theories continue to challenge conventional cosmology. Some suggest that our universe is not a singular entity, but part of a larger multiverse, a vast collection of parallel realities with varying physical laws, where what we see as the Big Bang was not the true beginning, but merely a transition from one state to another. Others propose that space-time itself is composed of discrete, fundamental units, like pixels on a screen, an idea that emerges from loop quantum gravity, a theory that attempts to unify quantum mechanics and general relativity by describing gravity as an emergent phenomenon arising from tiny, indivisible loops of space-time. If space is quantized in this way, then the concept of an infinitely smooth cosmic fabric breaks down, suggesting that at the smallest scales, the universe is composed of something more akin to a dynamic network of interactions rather than a continuous expanse. The role of quantum mechanics in shaping our understanding of the cosmos cannot be overstated. At small scales, quantum physics describes a universe that is probabilistic rather than deterministic, where particles do not have definite positions until they are observed, where entangled particles can influence each other instantaneously across vast distances, and where empty space itself is teeming with virtual particles popping in and out of existence. If quantum mechanics is fundamental, then the nature of reality may be deeply tied to the act of observation itself, raising profound questions about the role of consciousness in the cosmos. Could it be that the structure of the universe is not something fixed and objective, but something that is shaped by the very act of measurement? Could our perception of space, time, and even existence itself be merely one interpretation of a deeper, hidden reality? Changing viewpoints has always played a crucial role in reshaping scientific discussions. When Copernicus proposed that the Earth was not the center of the universe, it was met with resistance, yet it fundamentally altered the way we understand celestial motion. When Einstein formulated general relativity, replacing Newton's absolute space and time with a dynamic, curved, space-time fabric, it revolutionized physics and led to predictions that were later confirmed through observation. Today, we stand at the threshold of yet another paradigm shift, one that may require us to abandon our classical notions of reality and embrace a universe where information, quantum mechanics, and emergent properties define the very essence of existence. If we are looking at the universe the wrong way, then the true nature of reality may be something far stranger than we ever imagined, something beyond space, beyond time, beyond anything our current theories can fully describe. The next great breakthrough may not come from a new telescope or a more powerful particle accelerator, but from a fundamental shift in perspective, a realization that the universe is not what we thought it was, that the very questions we have been asking are incomplete, and that the answers lie in a new way of seeing, a new way of understanding, a new way of thinking about the cosmos itself. For centuries, we have sought to understand the universe by refining our models, sharpening our measurements, and expanding our observational reach, believing that with enough effort, we would eventually uncover a final, fundamental truth about existence. But what if the reality we have been trying to grasp is not what we thought it was? What if our most cherished assumptions about space, time, and the very fabric of reality are illusions, distortions, or even constructs of something far stranger than we ever imagined? In recent years, discoveries and theories have emerged that do not merely expand our understanding of the universe, they threaten to overturn it entirely, introducing possibilities so radical that they force us to reconsider everything we thought we knew. One of the most profound shifts in perspective has come from the growing support for multiverse theories, which suggests that our universe is not the only one, but merely a single bubble in an infinite cosmic sea of parallel realities. This idea, once relegated to the realm of speculative thought, has gained serious traction due to developments in cosmic inflation theory, which describes how the early universe expanded exponentially in the first fraction of a second after the Big Bang. If inflation happened once, there is no reason to believe it could not happen countless times, spawning an infinite number of other universes with different properties, different physical laws, and perhaps even different versions of ourselves living out entirely separate existences. In some models, every possible outcome of every event may be playing out somewhere, meaning that every choice we make, every moment we experience, is just one of an infinite number of possible realities. If true, this means that the question of the universe's edge is meaningless, because our universe would be just one of many, with no single boundary marking the end of existence. Instead, reality would be an ever-growing, ever-diverging fractal of possibilities, each one as real as the next, yet forever beyond our reach. But what if the reason we cannot find the ultimate structure of reality is because we are looking in the wrong place? Some physicists and technologists have begun to explore a possibility so shocking that it challenges the very concept of reality itself, the simulation hypothesis, which suggests that everything we perceive, from the vastness of galaxies to the deepest laws of physics, is not a physical reality, but a computational construct, a digital simulation running on a substrate beyond our comprehension. This idea, popularized by thinkers such as Nick Bostrom and even echoed by figures like Elon Musk, argues that if it is possible for an advanced civilization to simulate a universe, then statistically speaking, it is far more likely that we are inside a simulation than outside of one. Quantum physics, with its strange probabilistic nature, its reliance on observation to determine outcomes, and its seemingly arbitrary fundamental constants, may actually be a sign that we are living inside a programmed environment rather than a truly natural universe. The pixelation of space-time at the Planck scale, the seemingly arbitrary fine-tuning of physical constants that make life possible, and the eerie way in which reality seems to render only when observed, all lend eerie support to this idea. If we are in a simulation, who or what created it? Are we the product of an alien superintelligence running an ancestral simulation to study their past? Are we digital beings unaware of our nature, existing only as lines of code in a vast cosmic experiment? Or could we ourselves be simulations within simulations, layers of reality stacked infinitely deep with no true base reality at all? The unsettling possibility is that if the universe is a simulation, then the search for the ultimate laws of physics may be futile, because those laws may be arbitrary, designed by an external intelligence that can alter them at will. Yet even without invoking simulations, the discoveries of modern physics continue to challenge our fundamental assumptions. The nature of time itself has been called into question. While we experience time as a linear progression, relativity suggests that time is malleable, bending under the influence of gravity, And quantum mechanics hints that time may not even be fundamental, but rather an emergent property of a deeper, hidden reality. If time is not fundamental, then the idea of a beginning to the universe may be an illusion, just as our perception of past and future may be nothing more than a byproduct of consciousness interpreting information in a specific way. These radical shifts in thinking force us to confront the greatest existential questions. If the universe is infinite, or simulated, or part of a multiverse, then what does that mean for our place in it? Are we significant, or are we mere accidents of probability? Do our choices matter if every possibility is realized in some alternate version of reality? If we are simulated, does that make our emotions, thoughts, and experiences less real? Or does it mean that reality is simply defined by perception rather than material existence? Perhaps the greatest revelation of all is not about the universe itself, but about the limits of human understanding. The deeper we explore, the more we realize that the final answers may be forever beyond our reach, not because they do not exist, but because our minds, shaped by evolution to survive on a single small planet, may simply be incapable of grasping the full scope of existence. But maybe that is the true beauty of the search for knowledge, that even if we never find the ultimate truth, the journey itself, the endless pursuit of understanding, is what defines us, what makes us human, and what connects us to the infinite mysteries of the cosmos. Despite the remarkable progress we have made in unraveling the mysteries of the universe, the greatest challenges still lie ahead. Each new discovery, each breakthrough in cosmology and physics, has only revealed deeper layers of complexity, raising questions that current theories and observational technologies are unable to answer. As we stand at the edge of known science, pushing against the boundaries of human understanding, we must ask, what hurdles remain for future research, and how will we overcome them? The most pressing challenges come from both theoretical and observational limitations, forcing scientists to rethink fundamental principles and develop entirely new ways of exploring the cosmos. One of the greatest obstacles facing modern cosmology is the unresolved nature of dark energy and dark matter, two of the most dominant forces in the universe, yet completely invisible and undetectable by conventional means. Dark energy, which is responsible for the accelerating expansion of the universe, makes up nearly 70% of the cosmic energy content, yet we have no direct way of studying it. It does not interact with light or ordinary matter, making it almost impossible to observe except through its large-scale effects. The same goes for dark matter, which comprises about 27% of the universe's mass yet has never been directly detected. Without knowing what dark matter is made of or how dark energy operates, we are left with massive gaps in our understanding of cosmic evolution, structure formation, and the ultimate fate of the universe. Future research will require not only more powerful telescopes and detectors, but also entirely new theoretical frameworks that can go beyond our current models. Another challenge lies in the limitations of current observational technology. Even our most advanced telescopes, such as the James Webb Space Telescope, JWST, the Hubble Space Telescope, and Earth-based observatories like the Very Large Telescope, VLT, are still constrained by factors such as the wavelength ranges they can detect, their resolution, and the amount of cosmic dust and interference blocking our view of distant objects. JWST has already given us extraordinary images of the early universe, revealing galaxies that appear far more developed than they should be, according to our standard models. But even JWST is limited by the fundamental nature of light and cosmic expansion. There are regions of the universe so far away that their light has not had enough time to reach us, meaning that some parts of the cosmos will forever remain beyond our observational reach. To overcome these barriers, next-generation space missions will be necessary. The Nancy Grace Roman Space Telescope, set to launch in the late 2020s, will specialize in studying dark energy with unprecedented precision, mapping the large-scale structure of the universe in greater detail than ever before. The Euclid Telescope, launched by the European Space Agency, is designed to explore the effects of dark matter and dark energy by measuring the distortions in space-time caused by massive cosmic structures, providing insights into the nature of these elusive forces. Beyond optical and infrared astronomy, radio telescopes, such as the Square Kilometre Array, SKA, will allow astronomers to peer deeper into the structure of the universe, detecting faint radio signals from the earliest epochs of cosmic history. Yet, even these powerful tools may not be enough. Some of the most pressing questions in physics, such as the reconciliation of general relativity and quantum mechanics, the nature of time, and whether the universe is truly infinite, may require experiments that go far beyond what is currently possible. One proposed solution is the development of space-based particle accelerators, which would eliminate the constraints of Earth's atmosphere and gravity, allowing scientists to probe the fundamental building blocks of reality at energies far higher than those achieved by the Large Hadron Collider. Another idea is the creation of gravitational wave observatories in space, such as the planned Laser Interferometer Space Antenna, LISA, which would be able to detect ripples in space-time caused by some of the most extreme cosmic events, potentially uncovering new physics in the process. But technology alone is not enough. Theoretical breakthroughs are just as essential. One of the biggest questions in modern physics is whether space-time itself is fundamental, or whether it emerges from a deeper, unknown reality. Some physicists are exploring the idea that gravity, long thought to be a fundamental force, may instead be a consequence of the way information is encoded in the universe, an idea that could radically alter our approach to unifying quantum mechanics with general relativity. Others are working on alternative theories of gravity, such as modified Newtonian dynamics, MOND, and emergent gravity, which could provide new explanations for the effects attributed to dark matter without requiring an undiscovered particle. Scientists are also turning to quantum mechanics for answers, investigating whether the universe itself operates on principles of quantum entanglement and superposition, where reality is not a fixed structure, but a probabilistic, information-driven system. If quantum mechanics holds the key to understanding cosmic structure, it may mean that our classical notions of space and time are illusions, emergent from a deeper layer of reality governed by pure information processing. To tackle these unanswered questions, global collaboration will be critical. No single country or research institution can fully explore the mysteries of the universe alone, which is why international projects like the Event Horizon Telescope, EHT, which captured the first ever image of a black hole, demonstrate the power of coordinated scientific effort. Future breakthroughs will likely come from increasingly complex collaborations, where data from multiple observatories, particle accelerators, and deep space missions are combined to create a more complete picture of the cosmos. Ultimately, the hurdles facing future research are not insurmountable. They are simply the next challenges on our journey to understanding reality. But as history has shown, every time we think we are close to finding the ultimate answers, the universe surprises us with new mysteries, forcing us to rethink everything once again. Whether the future holds the discovery of a theory of everything, the revelation of an entirely new physics, or even the unsettling realization that some questions may never be fully answered, the pursuit of knowledge will continue, driven by the same relentless curiosity that has propelled humanity from staring at the stars in wonder to sending probes beyond the limits of our solar system. The greatest discoveries may still be ahead, waiting for the next generation of scientists to push beyond the limits of today's knowledge and into the unknown. At the heart of modern cosmology lies an ongoing battle between competing theories, each attempting to explain the fundamental nature of the universe while exposing the limitations of the others. This is not a battle fought with weapons, but with ideas, mathematical models, observational data, and philosophical reasoning, each vying to reshape our understanding of reality. The latest competing theories attempt to reconcile the conflicts between relativity and quantum mechanics, define the ultimate structure of space-time, and determine whether the universe has a true boundary, or if the search for such a limit is a futile endeavor. As we stand at the precipice of the unknown, the question remains, will we ever find the ultimate edge of the universe, or are we trapped within a cosmic puzzle with no final answer? One of the leading contenders in this confrontation is string theory, a bold attempt to unify all known forces by proposing that the fundamental building blocks of reality are not particles but tiny, vibrating strings existing in multiple dimensions beyond the three we perceive. String theory's greatest strength lies in its ability to incorporate gravity into the quantum framework, something no other theory has successfully achieved. It suggests that space-time itself emerges from the interactions of these strings, meaning that what we perceive as the fabric of reality may be nothing more than a low-dimensional projection of a deeper, multi-dimensional structure. However, despite its elegance, string theory remains largely untestable, with no experimental evidence to confirm its predictions. It offers a compelling vision of a universe where the fundamental forces are unified, yet without direct verification, it remains speculative, existing more as a mathematical framework than a proven physical theory. Opposing string theory is loop quantum gravity, LQG, a rival approach that discards the need for extra dimensions and instead describes space-time as a discrete, quantized fabric composed of tiny, indivisible loops. According to LQG, space itself is not continuous, but made up of fundamental building blocks, much like pixels on a screen, meaning that at the smallest scales, reality has a granular, digital structure. This idea challenges the classical notion of a smooth, infinite cosmos, instead suggesting that there may be a smallest possible unit of space, a fundamental limit to divisibility, which could have profound implications for our understanding of black holes, the Big Bang, and the nature of singularities. LQG offers a potential solution to the paradoxes of quantum gravity, yet like string theory, it has yet to produce definitive experimental evidence, leaving its validity uncertain. Beyond these attempts at unification, the debate over the boundaries of the universe remains one of the greatest unresolved questions in physics. The standard model of cosmology suggests that the universe is expanding, driven by dark energy, but whether this expansion continues forever, eventually slows down, or reverses in a catastrophic collapse remains unknown. The possibility of a cyclic universe has re-emerged, suggesting that the Big Bang was not a singular event, but one in an endless sequence of cosmic births and rebirths. In this model, the universe goes through cycles of expansion and contraction, meaning that instead of searching for a final edge, we should be looking at the universe as an eternal process, where each end marks a new beginning. This theory aligns with ancient philosophical ideas of cosmic cycles, yet it remains a challenge to fit within the framework of modern physics. Complicating matters further is the concept of the multiverse, which proposes that our universe is just one of many, each with its own physical laws, constants, and even different dimensions. In this scenario, the search for a boundary is irrelevant because each universe may exist in its own isolated domain, with no true edge in any conventional sense. The multiverse theory has gained support from quantum mechanics and inflationary cosmology, which suggest that random fluctuations in space-time could give rise to countless separate realities, each forever cut off from the others. Yet the very nature of the multiverse presents a scientific dilemma. If other universes are beyond our observational reach, can they ever be proven to exist, or are they simply mathematical artifacts of incomplete theories? Amid these competing models, the holographic principle has emerged as one of the most radical challenges to our perception of space and time. This idea, which originated from black hole physics, suggests that everything we perceive as three-dimensional reality is actually encoded on a distant two-dimensional surface, much like a hologram. If true, this would mean that the universe itself is not a vast infinite expanse, but a projection from a deeper, underlying layer of information. The implications of this are staggering. It would mean that space and time, as we experience them, are not fundamental properties of reality, but emergent phenomena, secondary effects of a deeper informational structure. This idea, though highly abstract, has gained support from studies of quantum gravity and black hole thermodynamics, yet it challenges everything we think we know about the nature of existence. As these theories battle for dominance, one question looms over the future of cosmology: will we ever truly know the final answer? Throughout history, every scientific breakthrough has led to new questions, new mysteries, new layers of complexity. The search for the edge of the universe, whether physical or conceptual, may be a journey with no destination, a quest where every discovery simply opens another door to the unknown. If we accept that the universe is infinite, then our search for its boundaries becomes an illusion, a problem of perspective rather than reality. If we accept that space-time is emergent, then the very concept of an edge may be meaningless, an outdated notion that no longer applies to the true nature of the cosmos. The future of cosmology will be defined by our ability to push past these limitations, to develop new ways of thinking that go beyond the constraints of classical physics. Technological advancements, from next-generation telescopes to space-based gravitational wave detectors, will allow us to probe deeper into the universe than ever before. Quantum experiments may reveal hidden dimensions or entirely new laws of physics. Theoretical breakthroughs may provide a unified framework that finally resolves the conflicts between relativity and quantum mechanics. But even with all this progress, the greatest challenge remains the limits of human understanding. Are we capable of truly grasping the full nature of the universe? Or is our perception forever confined to the boundaries of our own cognitive and observational limits? Perhaps the final confrontation is not between competing scientific theories, but between human curiosity and the unknowable. We may never find the ultimate edge, but that does not mean the search is in vain. The pursuit of knowledge, the desire to understand, the relentless questioning of reality, these are what define us, what push us forward, what make us more than just observers in the universe, but active participants in its unfolding mystery. Whether we find the ultimate truth or not, the journey itself is what matters, the ongoing dialogue between what we know and what we seek to uncover. In the end, the greatest discovery may not be the edge of the universe, but the realization that there is always more to learn, that the unknown will always call us forward, daring us to look beyond the horizon, to ask the next question, to never stop searching. The universe is vast beyond comprehension, stretching into distances so great that even light, traveling at its staggering speed, takes billions of years to reach us from the most distant galaxies. Every point of light in the night sky tells a story of time, of change, of evolution, and of forces far beyond human experience. Yet, for all the unfathomable immensity of the cosmos, the greatest mystery of all is not what lies beyond the most distant galaxy, nor what might exist beyond the edge of space-time itself. It is the question of why we, as humans, care about any of it. What is it that compels us to explore, to seek, to push past the limits of our knowledge into the unknown? The moral takeaway from our relentless pursuit of cosmic understanding is not just about uncovering facts. It is about the deeper truth that exploration itself is what makes us who we are. From the first humans who looked up at the stars and wondered what they were, to the modern physicists mapping out the fundamental laws of reality, curiosity has been the single greatest driver of progress. It is curiosity that led us to chart the heavens, to question the movement of celestial bodies, to break free from the notion that Earth was the center of the cosmos, and to embrace the idea that we are part of a much grander reality. Every major leap forward in science has come from asking questions that seemed impossible at the time. Whether it was Newton asking why the apple falls, Einstein asking what happens when you travel at the speed of light, or modern physicists asking what happens at the very edge of a black hole. These questions are not just technical. They reflect something profound about human nature. We are never satisfied with simply existing. We need to understand. Yet, as much as curiosity drives us forward, there is an inherent paradox in our quest for knowledge. The more we learn, the more we realize how much we do not know. The universe does not reveal itself easily. Every discovery, every answer has led to new questions, new uncertainties, new frontiers to explore. The realization that dark matter and dark energy make up most of the universe does not bring closure. It deepens the mystery, forcing us to admit that we still do not understand the fundamental nature of reality. The discovery that the universe is expanding at an accelerating rate does not give us a final answer. It forces us to ask why. Even the very nature of space and time is in question, as theories like the holographic principle suggest that what we perceive as reality may not be fundamental at all, but a projection of something deeper, more abstract. This balance between knowledge and mystery is what makes exploration so profound. It is not about reaching a final conclusion, a single equation that explains everything, but about the journey itself, about continuously refining our understanding and embracing the unknown as an essential part of the process. If there were no mysteries left, if every question had been answered, then the very thing that makes us human, the need to seek, to wonder, to push beyond our limits, would cease to have meaning. We are not meant to simply observe the universe. We are meant to engage with it, to be a part of its unfolding mystery. But the moral lesson of cosmic exploration extends beyond science itself. it teaches us something crucial about perspective, about our place in the grand scheme of existence. The more we learn about the universe, the smaller we seem in comparison. We are not the center of everything. We are a brief moment in an ongoing cosmic story, a species that emerged on a tiny planet, orbiting an average star in a galaxy among trillions. From a cosmic perspective, the conflicts, divisions, and trivial concerns that dominate human affairs seem almost laughable, yet this does not mean that we are insignificant. If anything, it makes our existence all the more extraordinary. In an uncaring, indifferent universe, we care. In a reality governed by physics and randomness, we seek meaning. This shift in perspective has the power to change how we see not only the cosmos, but ourselves. It forces us to recognize that we are all part of the same vast, interconnected reality, that the divisions we impose on nations, cultures, beliefs are small compared to the fact that we are all passengers on the same fragile planet, sharing the same fate. If the cosmos teaches us anything, it is humility, the recognition that we do not have all the answers, that we are not masters of the universe, but explorers within it. And in that humility lies the key to wisdom, to a way of thinking that prioritizes curiosity over arrogance, open-mindedness over dogma, and a willingness to embrace uncertainty rather than fear it. The greatest lesson we can take from our exploration of the universe is that the unknown is not something to be feared, but something to be embraced. It is in the unknown that the greatest discoveries await, where new ideas are born, where new civilizations may one day be found, where new ways of thinking will redefine what it means to be human. We must resist the temptation to believe we have reached the end of discovery, that we have already uncovered all that is important. The moment we stop questioning, stop exploring, stop reaching for the next frontier, is the moment we lose what makes us human. So what is the moral takeaway from our journey into the cosmos? It is that the act of exploration is itself the purpose. Whether we ever find the true edge of the universe, whether we ever discover a final theory of everything, whether we ever make contact with other intelligent beings, is not the ultimate goal. The pursuit itself, the act of questioning, of searching, of uncovering new layers of truth is what gives our existence meaning. The universe will always be larger than us, grander than our theories, more complex than our equations. But rather than be overwhelmed by its immensity, we should be inspired by it. Because as long as we continue to search, to wonder, to push the boundaries of what is known, we are doing something truly extraordinary. We are not just fleeting creatures lost in the void. We are explorers of the infinite. The question of whether the universe is open or closed, both in a physical and philosophical senses, one that has defined humanity's pursuit of knowledge for centuries. Should we expect to one day uncover all the secrets of existence? Or will the nature of reality forever remain a mystery, just beyond our grasp? In cosmology, an open universe suggests infinite expansion, where space-time stretches forever and galaxies continue drifting apart for eternity. A closed universe, on the other hand, implies an ultimate boundary, a point beyond which there is nothing, or a scenario in which the universe eventually collapses back in on itself, restarting the cosmic cycle. But beyond physics, this question has a deeper significance. Should our quest for understanding have a final, definitive answer, or is the pursuit of knowledge more meaningful when it remains open-ended? Some of the greatest mysteries in cosmology seem to demand answers, yet with every attempt to resolve them, new questions arise. The nature of dark energy, the existence of parallel universes, the fundamental fabric of space-time. Each of these questions points to deeper layers of reality that we may never fully comprehend. Some physicists and philosophers argue that the universe is fundamentally knowable, that given enough time, technology, and intelligence, we will eventually unravel the deepest truths of existence. The discovery of the Big Bang, the mapping of cosmic background radiation, the understanding of black holes, and the formulation of quantum mechanics all suggest that we are capable of profound insights, of peeling back the layers of mystery to reveal objective truths. Yet, for every answer we find, more mysteries emerge. And perhaps this is not a flaw in our understanding, but an intrinsic feature of reality itself. There is an inherent value in leaving questions unanswered. Mystery drives curiosity, and curiosity is what fuels progress. If we reached a point where there were no more questions to ask, would that not mark the end of discovery? The end of the very process that has defined human civilization? The unknown is not a barrier, it is an invitation. It is what compels us to explore beyond our own planet, to search for habitable worlds, to investigate the possibility of extraterrestrial life, to push the limits of what we know about space-time, black holes, and fundamental forces. The absence of a definitive answer does not mean failure, it means there is always more to seek, more to learn, more to uncover. Summarizing the biggest takeaways from our cosmic journey, we see that the universe is vast beyond measure, filled with forces and structures that challenge our understanding. We have discovered that the cosmos is expanding, that unseen forces govern its evolution, that time itself may not be fundamental, and that space may be far more complex than a simple three-dimensional void. The multiverse theory, the holographic principle, and the simulation hypothesis each present different ways of interpreting our reality, yet none offer a final, provable conclusion. And perhaps that is the greatest lesson of all. The universe does not owe us answers. It exists as it is, independent of our ability to comprehend it, yet that very incomprehensibility is what makes it so extraordinary. So, should the mystery remain open-ended? Absolutely. To close the book on discovery would be to extinguish the very fire that has propelled human progress for millennia. The infinite possibilities of space, whether they involve new physics, extraterrestrial civilizations, or unknown dimensions, are what keep us reaching, questioning, imagining. The greatest conclusion is, in fact, no conclusion at all, but an ongoing dialogue between what we know and what remains beyond our grasp. The universe is not a puzzle with a single solution, but a living, evolving mystery that invites us to explore, to wonder, and to embrace the unknown. And as long as we continue to look up at the stars and ask, what else is out there? We will never truly be lost in the vastness of space.